So welcome along, ladies and gentlemen, to your SETI, weekly SETI seminar series. Today we're joined by Erik Asphaug, who's come over the mountains from Santa Cruz to join us today. And he's going to be talking about collisions, which is the focus of his planetary sciences research. Erik got a BA from Rice in mathematics and English, and a PhD in planetary science from the University of Arizona. His interests are in the geological makeup of asteroids and comets. He has been using a Hydrocode simulation computer program to map the results of collisions and what we can learn from collisions in our solar system. He is particularly interested in hit-and-run collisions, which are, as I'm sure we'll hear, are collisions where the two bodies continue on their way rather than merging. Erik was also a member of the LCROSS team that modelled the impact into the moon recently in 2009. And he's also the PI of a discovery mission that he hopes to get up called Deep Interior, which will be used to go to a near-Earth object or asteroid and use radar to map the interior of the asteroid. So today he's going to talk to us about inefficient collisions, hits and runs, and splats. So if you'll join me in welcoming Erik.
Thank you, Adrian. I'm a big fan of the SETI seminar series. I show it to my students. There's some of the lectures are actually really valuable as educational tools, and so it's a pleasure to be here. And it's an interesting format. I have folks about a 180-degree phase angle, but fortunately there's two screens. And what I've been studying, what I'm going to talk about today, is research that goes back quite a ways. When I was a postdoc, actually I'd first come to Mountain View, work with Jeff Cuzzy at NASA Ames. I was supposed to model Saturn's rings, and to Jeff's great credit, he let me work on whatever I felt like working on, and I still probably owe him some research. But a comet Shoemaker-Levy 9 came along and was tidally disrupted around Jupiter, or had been. It was discovered after it had been disrupted as a string of pearls, and I got fascinated by this notion of things being pulled apart into chains of new bodies, and that led to thinking about collisions. Because even though planets, like these two planets you see in the picture here, they're not going to tidally disrupt if they pass by each other. They're quite massive, and the velocities tend to be too high. But they can collide and have this very complex interplay that's sort of a combination of tidal interaction, gravitational interaction, and good old-fashioned momentum change by inertia. You just run into something, and half of you stops and half of you keeps going. And so the case studies here, similar-sized collisions is just a generic term for giant impacts. And I call them similar-sized collisions because they are actually, it could apply for things that are smaller. Things that are 10 kilometers diameter colliding with another thing that's 5 kilometers diameter. That's a giant impact if it's slow, if it's kind of time similar. It takes order of hours for something to unfold in the gravity regime. So you can imagine planetesimals, 30, 40, 50 kilometers diameter, colliding at about 30 meters per second. That would be analogous to a giant impact. The physics would be quite similar to the moon-forming collision. And so case studies I'm going to talk about today. One is giant impacts, Earth, Moon, Mercury, Pluto, Charon in the outer solar system, diversity of bodies in other planetary systems that might result from these sorts of irregular aspects of these collisions. And then splats. These are things where things just hit and kind of splat into each other just like snowballs, making a cob house out of mud. And then this last thing that Andreas Reufer and I have been poking around with is coming up with a model for the origin of the Saturn system, which we're not sure what it's whether it's going to withstand the dynamical tests, but we at least have some scenario that has some geophysical appeal in terms of being able to explain some of the middle-sized icy satellites. So anyway, what are these collisions? Well, giant impact or similar-sized collisions, fundamentally they're slow. You think of the moon-forming collision as something fast. We talk about the shocks. We talk about 20 kilometer per second velocities because Earth's escape velocity is 11.2. So the slowest impact between Earth and another colliding body is actually supersonic. But they're slow in the sense that it takes days. It takes hours for the bodies to couple. It takes days for the ejecta to play out. It takes months for things to sort themselves out, and in the case of the Earth-Moon system, to form a moon. And so this time scale is quite long. A strain rate, which is the deformation rate, 1 strain per second would be sort of bending something like this. 10 to the minus 3 would take me an hour to deform something its own scale. And so these strain rates are quite low, and so rheology has a big effect. And so if you have small objects, I said these are just like giant impacts, they're not quite the same because for small bodies, rheology starts to matter, the behavior of rocks. And for big giant impacts, you can treat these objects as liquids. They're not, but big planets colliding, you can ignore strength effects. But at some transition size, strength effects start to matter. And then gravity is non-central. This is a very important phenomenon that you have two bodies that each bring comparable amounts of mass to the scene and changes the gravitational field. And so you have this very complex interplay of mass and gravity. Volatiles, shocks, compressibility, these are two aspects of the collision which have to do with the potential for losing your volatiles in a plume that's depressurizing and it's hot and it's expanding. Shock events, when you get above the sound speed, you start to convert basically kinetic energy of the impact into internal energy of the material, or heat. And compressibility, if things like comets collide and they have a porosity of 50% or so, you squash that porosity out, and that's going to allow you to absorb a lot of momentum, kind of like a crush bumper. In all of these cases, certain things are conserved. Energy, angular momentum are conserved, enthalpy is conserved. And so you can look at these conservation aspects of these collisions and see what they imply, as we'll do during this talk. And lastly, and probably most importantly, is that angular momentum is a big player because most collisions are off-axis. If you take a basketball and hit it with a soccer ball and try to hit them head-on, it's pretty rare that that's going to happen. They're going to bounce at about 45 degrees, typically. And when the things are about the same size and they hit at typical angles, about half the mass overshoots. Half the mass stops dead in its tracks, half the mass keeps going. And so that leads to a really sloppy scenario where most of the mass overshoots the target in a typical event. And disks, moons, and long-term ejecta can form. So going back in time a little bit, and this is a paper by John Chambers in 2004, so gosh, 8 years ago now. But he and others of his ilk, who are dynamical modelers doing n-body codes of planets forming out of smaller planets, the scenario we now think of terrestrial planet formation, at least, is hierarchical growth from smaller, maybe 100 smaller terrestrial-like planets, Moon to Mars-sized bodies that grow up. And what John did here is he sort of color-coded the inner solar system, where Venus is, Earth is, where Mars is. This is the stuff that they were made from, and this is what you ended up with in different simulation scenarios. Here's one scenario, two scenarios, three scenarios, four scenarios. And you can see that sort of Earth-like bodies tend to form mostly of Earth-like stuff, yellow and green. But they've got some mixes of inner stuff, outer stuff, water. You can think of that as water coming in from the outer solar system. Chemistry, if you look at the detailed chemistry of planet formation, the isotope systems that are embedded in the rocks of the Earth and the Moon and other planets we have samples from, the chemistry is a lot more complex than this. Planetary collision is not just simple merger, but for the winners, we're sitting on one of the winners. We're on planet Earth. Earth has one the battle. It accreted most of the matter, and it grew to such a size that nothing could bash it to bits anymore. Earth was finished at some point. It broke out of the pack, and these planets that break out of the pack, they become accretors. And this is really the story of the unaccreted that I'm going to talk about today. Sort of these small objects. I would say Mercury is one of them. Small planets, it's a really wrong assumption to assume that you just grow from some feedstock. You really go through a lot of mess to get to be a finished body. So here's some puzzles, and these have come up at recent meetings, and these are always on people's minds as kind of these weird, strange things. One, the moon is the mirror image of Mercury. This is as it was phrased at a recent conference. You know, the moon, as most of you are aware, is a rocky planet. It's made of rock that seems to be very similar to Earth's mantle, compositionally and isotopically. And then Mercury is a planet that has an enormous iron core. It seems to be missing at least half the mass of its mantle. And so you have this core planet and this mantle planet as some of the 5 major bodies of the inner solar system. And so this scenario that I'm going to talk about is sort of what's going on here. Seeing if you can separate the core from the mantle. Related puzzle is the iron bodies that we see in the asteroid belt. Psyche, Cleopatra are 2 large main belt asteroids that have densities and compositions that appear to be largely iron, although there's some debate about Cleopatra now. Then there are the meteorites from the iron parent bodies. We have 90 or more metallic iron parent bodies for the thousands of iron meteorites that are on Earth. You can go through and look at their alloy compositions and see that they come from 90 distinct groups or so. Where are those parent bodies? Why do we have so many exposed cores of asteroids? And then where's their mantle rock? The course should correspond to these asteroids. Bizarre objects in the outer solar system. I don't think I'll have time to get into these. But we have objects like Quasar, which has a density of 3 or 4 grams per cubic centimeter, which is a rock. You have a rock in the outer solar system next to objects that have densities closer to 2. So why this diversity of composition? Analogous to this diversity of composition, perhaps. Saturn's middle-sized moons, I'm going to end my talk with some discussion of a scenario for the formation of the middle-sized moons. But here you have these objects unique to Saturn that are about 1,000 kilometers diameter, a family of them, 6 of them or so. And they have ice-rich composition, but it's quite diverse, ranging from pure ice to about 50% rock by mass. Only Saturn has them. Jupiter has no satellite between 200 and 3,000 kilometers diameter. So where did these come from? Layered comets. There's this model by Mike Belton called the TALPS model, which is splat spelled backwards. And I guess when you're Mike Belton, you can invent new science words. And this is this idea that things could accrete by these unusual layered pile collisions. And finally, differentiated primitive asteroids. There's this notion of asteroids like Lutetia, which appears to have a relatively primitive, or whatever we think of as primitive, exterior composition, kind of a chondrite. And yet it has a density of around 3.5, which seems to belie a much denser interior, which seems to indicate a differentiated composition. So what's going on with any of these scenarios? And so we look at this mystery. Here's these planets that have had horrible things happen to them. And this, I think, is sort of like, cosmochemistry, sort of the fingerprint of what went on. And you can do a lot of detailed studies there. And then you can also look at the bullet. You can look at pieces of the bullet that came apart. And that's kind of the theme of the story here, is to look at the bullet. Because bullets do survive, and they do tell the tale. And so the notion of giant impacts, when I first looked into this around the time of Comet Shoemaker-Levy 9, and I was trying to think about, do planets interact? Can planets rip each other apart? And there was actually a very interesting paper by Alan Boss and Al Cameron, and they were looking at whether planets can rip each other apart tidally. And it was very interesting because they got to the point right where they're going to collide the planets and see what happens then. And they said, well, at this point there's a collision, and that's going to sort of result in accretion. So, and so that's kind of where this story picks up. It's like when things do collide, they don't actually accrete. And there's actually this whole playing out of this scenario. But if you think of it in these terms, this is kind of a standard model for how the solar system evolves. First, you have slow velocities, and planets grow into planets. And things tend to result in mergers. Things grow, they get big. And then you can't destroy anything that's at the high end of the size spectrum. It's just impossible because the velocities are low. You have to have a lot of kinetic energy compared to your gravitational binding energy to break something apart. And then you have higher random velocities later, especially for the smaller bodies. This is all relative to the escape velocity of the object being destroyed. And so if you increase the kinetic energy relative to the binding energy, then you can have this epoch where things get broken apart. So you make things, then you break them. And what we're looking at when we see meteorites are broken bits of planets that were made. And there's two separate time epochs. But as we'll see, there's this vast middle ground of non-accretionary collisions that occur at the dynamically relevant velocities. These random velocities, when planets form, the random velocities are kicked up by the escape velocity of the biggest object plowing through the swarm. And so this is kind of a nominal condition for during planet growth. You can have speeds higher and lower than this, and I'll show you a general parameter study here in a moment. And this results in a couple of different kinds of collisions. One, hit-and-run collisions, where, as Adrian said, it's two things colliding and one thing continuing downrange. And inefficient merger, also called graze and merge. And this is actually quite common when things hit at around the escape velocity at around 45 degrees. It first bounces off and then comes back and hits again, and might bounce 3 times or even 4 times, and things spin out. And folks who study stellar collisions or galactic mergers are very familiar with this. You know, the center of mass clumps, and then as a result, the gravitational potential changes so that it can slough off exterior material. And you can lose a lot of material, even though the collision is at close to the escape velocity. And then looking at the projectile bits that survive downrange gives you this idea of a new kind of catastrophic disruption where you're destroying the projectile and you're looking at pieces of it. So when you look at pieces of a meteorite, I would claim you're looking at pieces that crashed into a planet and got ripped apart at some point. And I'll show you the statistics that I think proves this. And so when the colliding bodies are similar sized, okay, here's planets in our inner solar system, including the moon. Here's asteroids, in the 4 largest asteroids. We've never seen Ceres, and now we have better pictures of Vesta. But these are to scale. When things are about the same size, simply they miss. And you have this big fraction of the bodies flinging off at the outside, even for impact angles of 30 degrees. This is a 30-degree collision with a mass ratio of 2 to 1. Half the mass overshoots. And this is pretty close to head-on. 30 degrees is more head-on than average. At 45 degrees, shown over here, most of the impactor actually misses. And so these types of impacts leave a lot of mass downrange. If they are slow, if they are pumped up to about the escape velocity of the pair, which appears to be the case for most studies of planet formation. So, for example, Agnor et al. 99, O'Brien et al. 2006, Raymond et al. 2009, they get typical collision speeds during planet accretion of about 1 to 3 times the escape velocity. So ranging from 2 things just falling from infinity onto each other to things that are excited to about 2 or 3 times that speed. And this can be very slow in the case of mergers. And so you've been patient, so I can show you a movie. This is by Andreas Reufer, who's a postdoc from Willy Benz's group at the University of Bern. And what you're watching here is actually Titan, the simulation of a Titan-like body being hit by a planet about 1/3 of its mass. And this would be counted as accretion. This would be counted as a perfect merger if you were running one of these n-body codes. You'd say, well, there were these 2 bodies, now there's 1. And that's true. Titan does gobble up most of this object, but it slings off all these bits. And you can notice that some of the bits actually have bits around them. There's actually, it's hard to see here, but there's actually satellites around the satellites. And then this guy here, I think you're going to get satellite around the satellite around the satellite, which is orbiting Saturn. So it's, and then that plays out dynamically to pretty rapidly, because this orbital period around Saturn is 16 days or so. And so in the course of a billion years, this is all going to settle out. You can play with impact parameters. Here's much more grazing collision. This is 80 degrees off axis. And now the thing, it basically it hasn't had much happen to it. And then it gets back into the Roche limit. And then you sling off these spiral arms. This is very reminiscent of stellar mergers. And you have this array of clumps of mostly ice material that fling off. So during this growth, so that's the process I'm talking about. And is it important? Well, let's consider the inner solar system. So we've addressed these geometric factors for these kinds of top of the food chain collisions. But consider Earth and Venus. There's 17 Mars masses inside of Earth and Venus. And there's 2 Mars mass planets left, Mars and Mercury. And let's consider Mars and Mercury. They have 13 moon masses, but there's only 1 moon mass planet left. And so a rule of thumb is 90% of the bodies the next size down have been accreted. Okay? So 90% have been accreted, and it makes you think of like one of those war movies, or the war itself, where 90% of the soldiers, only 10% come back. And here's this famous, the best graph in the world, supposedly by Charles Minard. And this shows Napoleon's army heading for Moscow and then coming back. And so when you're looking at Mars and Mercury, or at the moon, you're looking at this guy. The end of a great campaign. Most of them were accreted by the planet that's bigger. And so this notion of what you're looking at today when you're looking at these minor planets is very strange in this context. And you can have highly diverse outcomes for each of these collisions. Here's one by Martin Jutzi, also from Willy Benz's group. By the way, Andreas Reufer is now going to become a pilot for Swissair. Martin Jutzi is going to work at the patent office where Einstein worked. And so I think there's this pathway for numerical modeling to other fields. But this is a beautiful piece of research where the impactors coming in lead to these chains of bodies going out. This is a study that we've been pursuing to try to form, basically trying to get the core out. This issue of all these iron meteorites, what are we doing with all these irons? Well, red is core material, and we're trying to sort of see if we can eviscerate planets. This is the impactor. This is not none of these are pieces of the target. These are all pieces of the impactor that got broken apart into a chain. Again, reminiscent of Shoemaker-Levy 9. And so if you do a bunch of these simulations, and this is work Craig Agnor did back in 2002, 2004, and we did a series of calculations for impact angles of 0 degrees in black, so head-on collisions are black, 30-degree collisions are blue, 45-degree collisions are red, and more grazing, 60-degree collisions are green. These are mostly 25% probability quadrants. You can think of each of these as being equal probability. And then square is 1-to-2 mass ratio, triangle is 1-to-10 mass ratio, and circle is 1-to-1 mass ratio. So there's different kinds of impact parameters, impact conditions, but the general trend is as you go from random velocities of 0, that is, things just dropping in on each other, you have efficient accretion. As you excite the dynamics with time, for example, big planets grow and start to shake things up, or you have perturbations by giant planets, or if you have some damping forces velocities to be slower or faster, you go rapidly from this efficient accretion, partial accretion regime, you drop down to an accretion efficiency of 0, which basically means 2 bodies collided. And what's the mass of the final body? Well, it's the same as it was to begin with. You did a lot of bad stuff to it, but it didn't lose mass, it didn't gain mass. It might have swapped some mass. But and it's interesting, they fall down on these lines and they hug this line. And that sort of is this condition between hitting and sticking around and going downrange. And so a lot of collisions. In fact, this is about easily half of all collisions in the interesting dynamical regime of about 0 to 3 times the escape velocity. That's what people see when they do n-body simulations of planet growth. It's operating in this range. About half of them are these kinds of hit and runs. And so if you put that together, well, here's one of these models. This is by David O'Brien, his simulation in 2006. Impact velocity, velocity at infinity divided by the escape velocity goes between about 0 and 1.5 or so. And so these collisions, by the time they actually impact, you add the escape velocity to that random velocity, you get a collision velocity that's down around in here. And so it's a relevant regime. Sarah Stewart and Zoe Leinhardt earlier this year, they published this more systematic exploration of these regimes, and they divided out hit and runs from graze and merge. Now, graze and merge, there's nothing different between graze and merge and hit and run, except that graze and merge slows it down enough that it reaccretes the material afterwards. Hit and run, it just keeps escaping. And so this distinction as a function of this is the impact velocity divided by the escape velocity for a 1-to-1 mass ratio, 1-to-2 mass ratio, 1-to-10 mass ratio, 1-to-50 mass ratio. You can see that this dominates. And that has important consequences for the planets that have finished forming. And if you make a very simple model, which is kind of the fun type to do sometimes, and you just say, let's start with 100,000 initial planets, and let's just pairwise accrete them in the simple way of just randomly picking 2 and seeing if they merge, and that's not right. But it gives you some idea that as you grow these things, by the time you end up with 1,000 bodies, the little black dots here, a lot of these have experienced 4, 5, 6 hit and run collisions. Of the survivors, everything that's accreted, I've taken away from the list. It's become part of a bigger planet, and that planet's grown. So this is kind of a simple accretion code. And then by the time things have grown to 30 bodies, you have some objects that have had 12 hit and run events. What that means is the same object has been trying to accrete, and so you think of like that fish in the pond in the summer. It's been on the hook, 10 times by the end of summer, and it hasn't taken it yet. And so there's some planets that have had this string of bad luck. They eventually get accreted. That's why these go away. It merges into the body of something bigger eventually. And this is a random, it's a Monte Carlo type analysis. But in the end, you have these final big bodies that have all had of order 2 to 4 hit and run events by the time you quench the system. And by quenching the system, what I mean is you get rid of anything bigger that they could accrete into. And so the asteroid belt today, where planets once roamed, we are pretty sure Moon to Mars-sized planets were part of the main belt at some point. And when those planets were gone, you're left with big objects that are stranded there. Now, this is a simple model that assumes half the collisions are hit and run. You could play with that notion a bit. But it leads to this thesis where a solar system forming by pairwise accretion obtains a division between the accreted bodies, Earth, Venus, say, those which made it to the top of the food chain, and they're homogeneous byproducts of their feeding zone, like the pie charts of John Chambers that I showed very early on, and the unaccreted bodies, which are against all odds. 90% of them merged, and 10% of them didn't. And so what you're looking at are these bizarre things. And so the quote from Anna Karenina might be applicable. So the collision process, let's look at some of these, how this plays out. Collisions are represented by mass and gravity, by the momentum coming in, the angular momentum they've got, including the spin states of the planets themselves. This is important, and we haven't, that opens up a huge parameter space that we haven't been systematically exploring. But you have, and then you have energy. You have the kinetic energy coming in, you have the internal energy of heat. Extra heat is generated by shocks. And then you have size, composition, and structure, which matters quite a bit in collisions. If you're a differentiated planet, when you collide, let's say I'm a rocky planet with a massive icy core, and I collide with something else that's rocky with an icy core, what's really colliding are our icy mantles, and our cores come along for the ride. And so the cores can actually have this almost a tidal gravitational evolution that's almost separate of the shock event happening to the icy mantles. And so the size, composition, and structure of the bodies matters a lot. As you can guess, you can't just write down an equation and solve this. So we represent this on hydrocodes. And so there's a number of grid-based solvers that are used. These are challenging to use in the case of collisions because you have to grid up the problem domain. You have to basically grid up the space into which all the debris is going to expand out into. And so the code technique that I've been using and all the colleagues that I've shown pictures of their simulations so far is called SPH, Smooth Particle Hydrodynamics. And its advantage is it has no grid. All the mass is represented by individual particles, and the pressure forces and other forces are represented by basically making a grid out of the particles and doing a kernel sum in order to get densities and pressures. And the disadvantages, there are some instabilities known to SPH. There's clumping instabilities that we have to be very careful of. And there is interfacial behavior. If you have particles adjacent to each other that have vastly different densities, that can introduce some inaccuracies. But there have been great advances in the past 10 years, and so these codes have become quite popular. And the challenge is that movies are overly convincing. I think that it's the modelers' onus to basically not just click on the plot and say, here's our stuff, but to actually go and analyze whether, recognize that it's a mathematical system being evolved, and that you have and that it's physical. And one of the humbling aspects of this is that you do this kind of collision. This is a simulation of the moon forming impact, the giant impact that formed the moon, done by Robin Canup and myself, and many others earlier. I think Willie Bentz was the first to model this with SPH with a hydrocode, and Kip and Malash did this with a CTH way back when. And but the basic scenario of a giant impact has been around with us for some time. But two things: different models are giving different results. And when you think about the moon-forming collision, what you're trying to model, you're trying to come up with the accurate representation of the 1% of the debris that went through the worst, most numerically inaccurate part of the problem. The hottest debris that accretes then to form this little nugget orbiting the Earth, 1% the mass of the Earth. In a cratering calculation, you probably wouldn't really, bet a whole lot of beer on the fact that you modeled that part correctly, but here that's what you're trying to capture, is this essential aspect of the event, the hottest ejecta. And so different codes give slightly different answers, but they all give the basic fundamental conclusion that a Mars-sized body striking the Earth makes a disk that's about a couple of lunar masses. And there's some fundamental problems with the model, though, because the oxygen isotopes of the Earth are dead ringers for the oxygen isotopes of lunar sample rocks. And the bulk composition of the moon resembles the Earth's mantle. But the isotopic similarities indicate that these simulations have this fundamental problem that the moon tends to form mostly from projectile material. So what's the moon doing with Earth composition to like the 4 significant figure level if it was made of a different body? And so here's from Polemon and Stevenson's assimilated a bunch of different data for the isotopes of Mars and the Earth. This is delta 17O versus delta 18O. These are the oxygen isotope trends. And the Earth and the Moon are indistinguishable. And a planet like Mars lies way off the line. And you'd expect the Moon to lie somewhat off the Earth line. Andreas Reufer and Willie Bentz have been working on this. This is a paper in preparation where you have, basically they're doing the same kind of calculation that's been done for a while. This is their new twist on it, changing the parameters a little bit. The name of the game is, can you make the moon mostly from the Earth? That's the name of the game right now. And they can make the moon 80% from the Earth. And the way they make it 80% from the Earth is they take this impactor coming in, and a big chunk of the mantle of the impactor actually escapes in this particular parameter. So it gets rid of the rock composition problem by throwing away the rock you don't want. And then this thing comes back and hits the Earth again and spins off mostly Earth mantle. It gets you close. It gets you to 80% of the moon is composed of, or the moon is composed 80% of Earth rock, 20% of Theia, which people call the impacting body. And is that good enough? I think you need to get around 90, 95% to really get in those realms. Here's a different kind of a code model. This is by James Guillochon at UC Santa Cruz. He's a student there who's more familiar. he likes to throw stars at black holes. And so, we got him interested in this problem. And I just like this simulation because this is a grid-based code. And so I think we're going to enter an era, or we have entered an era, where people are trying a lot of different kinds of numerical techniques for the same kind of problem. It's interesting. You see this big wave. This is the core of the impacting body. This is the mantle of the impacting body, and it's a mess. But what's interesting here, when Robin and I were doing these simulations, what was quite interesting was we had a lot of runs where we didn't make a moon. The impactor went on its way, and we were like, oh, that was wrong. You do it again, try something better. And we ended up at, this was it was kind of funny because after trying to exhaustively explore parameter space to make a moon from a giant impact, we ended up with pretty much the parameters that Hartman and Davis and Cameron and Ward had come up with originally. About a 45-degree off-axis impact, about the mass of Mars, coming in at about escape velocity, did the trick. But again, we had this compositional problem, which didn't exist at the time, or we didn't know about it at the time. But what's very interesting is we found that impacts that are a little bit faster, about 30% faster, they bounce off. So here you can see the impactor coming in, and it does bounce off. This is the main mass of the impactor right at this knuckle here. And then there it's coming back. And then it hits a second time and shreds this thing. And you can see the side view. So this is what would now be called a Grazen merge collision. So what happens when things are a little bit faster? Well, when things are a heck of a lot faster, you can do pretty bad things to a planet. Here's a model by Willie Bentz and colleagues for the problem of making Mercury. Mercury, the issue is analogous to the moon, except instead of having something that's mostly mantle, you have to have something that's mostly core. How do you get a planet that's mostly core? Well, bash it. The planet's finished, and it's the biggest object in the room. So trying to get the mantle off of a finished planet requires an impact of enormously high energy. And so here's a typical case. This is from Onyx's thesis and at the University of Bern. And you see that boom, 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 boom. And by the time the things have finished colliding, you've got this naked core. The mantle of Mercury has been entirely disassembled. What have you hit it with? You've hit it with something about 20 to 35 kilometers per second, 4 to 7 times the escape velocity. To go back to say what that means, the escape velocity, you're talking about impact velocities up here, really at the top of the chart. You're talking about top of the chart collisional velocities happening between something quite large in the inner solar system. And the problem is fundamental in two respects. One, where did this object come from? Well, maybe from the outer solar system, a wayward body. You do have them. You do have odd events, and Mercury could have been hit by such an odd event. The second problem, I think, is a little bit odd, that the moon forming event should involve the slowest possible collision, right around escape velocity, a Grazen merge collision at 1.05 the escape. And the Mercury forming event should involve a giant impact at 4 to 7 times the escape velocity. You have collisions at the two ends of the bell curve, explaining these oddities. So what? Oh, and the last thing is Mercury actually is not devoid of volatiles. There's a lot of news about this from the Messenger mission. And yet, if you spray a planet's mantle around the sun and then reaccrete it at late time, it's a pretty good way, it seems to me, to cause it to lose a good fraction of its volatiles, at least make it look more lunar in composition. And so what if you have something happening slower? And this is just a conjectural plot. There's no model here yet. But here's a hit-and-run collision between two objects that are 2-to-1 mass ratio, impact velocity of 1.4 times v escape, and the little guy loses half its mantle. This is a collision at 1.4 times v escape, so it's in that same realm of gradual of low velocity collisions. And except you're not doing anything to the target. You're not blasting mantle off the target. It's impossible. The amount of energy it takes to blast a huge amount of mantle off a target planet is just off the charts. But to get the mantle off an impacting body is fairly easy. So just the conjectural picture, Mars coming in, Mercury going out. And you have much lower shock levels because the velocities are slower. So that's the rest of my talk will be these vignettes, and please raise your hand if you have any comments or questions about them. But this is sort of one vignette, is you could make Mercury in a low velocity collision. What you have to do, of course, is have some dynamical instability relatively late, play itself out. And if you talk to Hal Levison and dynamicists and folks like Matja, who's sort of the dynamics cop, who says you can do this or you can't do this, I think you got to talk to the dynamicists, because here you have to, excite proto-Mercury into some collision involving Venus. Or you could imagine that dynamical velocities. You could imagine, for example, where Mercury formed has a lot to do with this. Perhaps Mercury had a slightly more excited collisional environment, so more collisions were hit and run where Mercury accreted from, and more collisions were accretionary, where Earth and Venus accreted from. And so something accreting out of bodies in this environment, they're going to evolve to have high, what I call H numbers, hit and run numbers. You're going to have Mercury forming out of objects that have had many hit and run events, and then they might have lost their mantles hierarchically instead of as one wallop. So this notion of a single Mercury forming wallop is conjectural. It could have been just the way Mercury grew out of hierarchically out of smaller bodies, which also did this kind of a process. Okay, I said I would talk about splats. This is a simulation where, well, this is kind of a funny story because Mike Belton has this TALPS model that I told you about, where comets formed by splats, and he had given up on his own model, and I actually like his TALPS model, just because it's splat spelled backwards. But he has actually been looking at different models for layered structures on comets involving interior volcanism, basically. You have elutriated sediments laying themselves down as debris flows, but we hadn't given up on it yet, and so I told Mike that we were going to try to model a 5-kilometer comet hitting a 2-kilometer model comet. And so Martin Jutzi, now back at the University of Bern, we had done some simulations and made layered pile comets. Basically you could have done it in your backyard with snowballs. Well, not here in Mountain View, but somewhere. You can splat these things together. And so we were trying to understand the asymmetry of the lunar crust. And there was a couple of models out, one by Ian Garrick-Bethel and his colleagues, Francis Nimmo and Mark Wazorek, explaining the lunar farside highlands as a frozen-in tidal bulge. You have moons much closer to Earth, you have a big tidal bulge. The problem is only the far side of the moon has a bulge. The near side of the moon is flat. Thin crust on the near side, thick crust on the far side. You freeze in a tidal bulge, you freeze in 2 thick layers. You have the basic symmetry of tides would give you 2 layers. And so I didn't quite understand how you're going to get rid of the other side of the moon's crust. And there are ways you can do it, and that's being worked on by Ian Garrick-Bethel and his students. Trying to later have a core asymmetry and have a convection interior to the moon, preferentially eroding the near side of the crust. So you can get that to work. But give the man a hammer and everything looks like a nail, as Hal Levison says. And so we say, well, let's try whacking some things together. And the thing about low velocity collisions, very low velocity collisions at the escape velocity, is that everything stays behind. You don't have any downrange material at all. So this is a collision at about 45-degree impact. The smaller moon is made of the same stuff as the bigger moon because they formed in the same giant impact. And the notion here is that you manage somehow to delay their accretion late enough in the game that the moon had solidified its crust. This little ball solidifies in about 1 million to 10 million years. It's a ball of rock by that time. And the moon probably is largely solid within 10 million years. And so you basically have 2 objects that are solid crashing into each other, and you get a big mound of material about 30 kilometers thick. What was a cute aspect of this splat model was that then we said, well, wait a second, the moon's not entirely solidified. It actually has this melt layer called creep, potassium rare earth element, phosphorus-enriched melt. That's basically the last residual melt. Everything else is solidified and crystals have sunk and floated, and what's left is this creep layer that persists to fairly late time. The last stuff to freeze takes a while. And there's this mystery of why do you only have creep on the lunar near side, or primarily on the lunar near side? Well, the impact displaces the creep, kind of like you threw a cantaloupe on top of a jelly-filled crepe and just squished it all to the side. It's very simple mechanics. You could do this as a scaled experiment with mud and jelly and things like that. And Martins has a great gift for rendering his computer models. Another graze and merge is the formation of the Pluto system, work by Robin Canup recently, 2008 and 2010, forms Pluto-Charon and a low-mass disk to get not only Pluto-Charon, but also this disk of material from which the moons of Pluto would form. I think I think it's right. And it makes a great deal of sense because collisional velocities in the outer solar system are quite slow. But again, in science, we all start to get our blinders on. And so I think that collisional modelers, we need to get out more. But chondrules, the next vignette. These are, I actually printed this out as a really big picture. I like to go to, I don't actually have any meteorites, so I go and print them out on the web and pin them on my wall. And this is a meteorite probably about 4 times real, maybe 10 times real life. And these are, what's a mystery here is if some random meteorite were to crash through the ceiling and land on the ground here, we ran to pick it up and we sliced it open and etched it. Chances are, 8 or 9 out of 10 that you'd slice it open and you'd see this structure inside with all these little BBs, all these little spheres. And these are, early original little spherules. They have ages of about 1 to 3 million years after the first solids, although the dating is quite tricky in that early regime. You have some bigger chunks, some smaller chunks. It's been through a lot since. It's all fractured and beat up. And if you look closely at some chondrules, here's 2 chondrules that collided and merged, kind of like their own, graze and merge event, scaled down to microns or millimeter scale. And so these were molten when they reaccreted in some swarm. And then you have these interesting aspects like iron tends to armor some of these chondrules. And the things that you have to explain in chondrules, like giving a chondrules talk, and we have 2 chondrules experts out here. You could spend probably a whole year-long course describing some of these puzzles that you're trying to explain with chondrules. But and it's easy to conceive that they form by more than one mechanism, both collisionally, like the CH chondrites and the CB chondrites. People are starting to believe that these formed actually by collisional events. And then the rest of the chondrules, the ordinary chondrites and their chondrules, seem to, there's ideas that they might have formed in the disk through some kind of a shock process. But you've got to explain a whole array of processes. And I'm not going to get into the details other than to point out a few of them. You've got to explain that they're about the same size. They're little, millimeter-sized BBs. Why are they so abundant? They comprise most of the mass of chondrites, which are the most common meteorites that fall to Earth. Why are they liquids? What are liquids doing in a low density nebula? They cooled quite fast. So if you take a BB, or if you ever have, played with solder, I have a 10-year-old son who likes to solder things and he likes to play with a little drop, and it takes like a few, tens of seconds to cool, right? Little solder droplet. But the chondrules took hours to cool. And so there's this cooling issue. What kept them from cooling? And so this notion that they formed in very dense swarms, so they couldn't freely radiate to space. But then that dense swarm had to expand over a time scale of hours or days. And so on. The problems are enormous. And so one of the concepts that you can explore from a collisional point of view is maybe they can form during accretion as a thrown-off aftermath of an accretion event. So the notion that they had to form in dense self-gravitating particle swarms, I think, has been pretty well defended. And a dense swarm, might be something that's already gravitationally bound. And so looking at planetesimal collisions now, giant impacts involving 30-kilometer bodies, 50-kilometer bodies, 100-kilometer bodies, you can start to look at the spray of material from a low-velocity collision. These are collisions at the speed of a car crash. This is early accretion events. Speed of a car crash, maybe 100 meters per second. A race car crash. And the objects are about the size of the state of Rhode Island. And so these are, it's a realm that hasn't been explored physically in enough detail. But the stuff that accretes, and here you can actually see this little red crescent. This is the core of the impactor accreting, and the rest sprays downrange. If you say, I don't know how many of you have done this, but you take coffee in your mug and it's cold, whatever, you toss it out on the grass and it disperses into droplets. That's a complex interplay of phenomena. There's two processes going on there. One is interaction of a film of water with the air, and it gets ripped apart by instabilities, density instabilities. And then the other aspect that's going on there is you've forced it in your cup, so you've kind of increased the pressure by throwing it out there, and then that pressure drops again, and you can start to form droplets by this pressure unloading. If you've ever looked at, I don't know if you're a big fan of space station videos, but they have these water dumps where they throw wastewater out overboard, and it atomizes into droplets. And so going from high pressure to low pressure, you conserve enthalpy. That allows the conversion of that enthalpy into surface energy. And so this is kind of a complex notion, but here's a snapshot of one of these collisions after the fact. And the two bodies have merged during accretion. And what goes downrange is this low pressure sheet of material. It's gone from tens of bars of pressure down to zero, or close to zero. You've thrown it into the nebula. What happens to the enthalpy? Well, it can degas. It can undergo phase transformation. It can undergo dissolution. All those kinds of things require surfaces. You can't degas without surfaces. So the limiting aspect is this opening of new surfaces, which is atomization, forming droplets. And so if you go a pressure drop from tens of bars to 0 bars, going from before it was happily inside of a mantle, after a few hours later it's atomized into droplets, you can get an equation for the characteristic droplet size you should expect from throwing mantle material out into space, essentially. And what was kind of neat was that for 10, 20-kilometer diameter planetesimals, you could get chondrule-sized droplets in this kind of a process. Now, this is a very coarse approximation of what really happens. I think in actuality, you form droplets that are much smaller, and in this plume, then they accrete, and they grow into bigger droplets that form the chondrules. But this vignette, I think, concludes just with this notion that there's this process for making kind of a nebular phenomenon. You're throwing this stuff back out into the nebula, and it takes hours to days for these droplets to coalesce back into objects. And it just basically goes to show that you can make exotic rock textures through collisions. And I'm running close to time, so I wanted to end with this notion of the late origin of the Saturn system, which is trying to explain this strange phenomenon that Saturn, as I mentioned earlier, has 6 bodies around 1,000 kilometers diameter. Jupiter has none, and I don't think anybody has a good explanation for that. I think that it's a real bizarre aspect of the Saturn system. And furthermore, in 2008, 2011, and recently Nimmo and Korokonsky have an abstract and then a paper showing that the late heavy bombardment, this flux of impactors that should have occurred during the perhaps playing out by dynamical instabilities in the inner and outer solar system that might have contributed to the heavy bombardment on the moon, these should have vaporized these middle-sized icy satellites. And probably did so, I guess, at Jupiter, because it doesn't have any. And then other aspect of this is that they are purely ice-rich. And so if it destroyed these middle-sized moons at Saturn and elsewhere, how did Saturn end up getting a new family of them?
What size are you saying would be vaporized?
Things like 1,500 kilometers and smaller, and that's actually Korokonsky's.
Jupiter or at Saturn?
At Saturn.
1,500 kilometers get vaporized at Saturn?
Well, that's on the large size.
Yeah, yeah.
Like, 500 to 800.
Yeah.
You lose a lot of mass.
Yeah, they lose a lot of mass. And then and they get rockier. They get driven to rockier composition, probably. Yeah.
You might be able to do that for some by claiming that you cleared Jupiter that way and not Saturn that way.
Yeah.
It's based on pure luck. I'm not sure you're not picking a size and you're not picking an energy. So it's hard for you to then conclude that Jupiter is different from Saturn for that reason.
Well, it might not be different from Saturn for that reason, but it's different from Jupiter for some reason. And so this, I grant you that. There are many other ways that you can skin this cat. This is one scenario that's been trying to explain. How do you have this ice-rich material in the Saturn system? And so one notion is that Saturn somehow kept them. They were lucky. There is some ways to be lucky. You could park the ice somewhere in a massive body that was too big to be disrupted. Or Saturn somehow made new ones. And there's a couple of ways to make new ones. And one is to start with a huge amount of ice. And so Robin Canup has a model where a Titan-like moon early on spirals into Saturn and erupts tidally into an ice disk. Massive ice disk made out of a Titan-like body's mantle. And now you've repopulated, or you've populated the inner system with a huge amount of ice, about at least an order of magnitude, a factor of 20 or 30 more ice than is there today. And that's survived into the present. And it survives the late heavy bombardment. And then the question is, where is this massive ice disk at Jupiter? I think that's still a valid question, that you've got planets spiraling into Jupiter as well, early on. Moons the size of the Galilean satellites. So Jupiter should have started off with this massive disk as well. So the question is, can you inject a bunch of ice from somewhere after the late heavy bombardment? Or, around the time of the late heavy bombardment, but have it survive to late time. And so this is a model that we've been playing with, Andreas Reufer and myself. This notion of Titan accreting a satellite late in planetary history, relatively late, in the at least 500 million years after it all got going. And so just to give you sort of a picture of the sizes, here's Tethys, although there's a projection effect. Tethys is actually about a fifth the diameter of Titan. And then sort of an icy, mostly ice-rich, similar composition to Titan object, about half Titan's diameter, or a little bit bigger, accreting into Titan. And so here's this accretion. And the reason why we're intrigued by exploring this scenario, we're not compelled by the dynamics. I think it's a little tricky to get this to work. We're not compelled solely by the fact that Jupiter and Saturn are so different, but we're compelled by the fact that Saturn alone has a population of satellites of this size that are almost pure ice. Well, they range from 50% weight rock fraction to 100% ice fraction. And they have very similar sizes. And if you plot the results, here's the satellites of Saturn, the middle-sized icy satellites of Saturn. Iapetus is an outer moon, so this would be kind of hard to make by this process, possibly. But here's the end outcomes of different kinds of results, rock and ice fractions. And we get pretty good fits. And we haven't started to twiddle yet. We haven't really started to dial the knobs on the model. We just started with Titans and hit it with things and tried to see if we could get something that looked reasonable. And you get diverse compositions. You try this at high velocity, you start to get rockier and rockier compositions because you're driving more rock out of the middle of the target. And you do this at low velocities, and they're more icy compositions. So there's a range of possibilities here. You look at where they came from. So Tethys, if you wanted to call our biggest one Tethys, comes from the icy crust and ocean. Enceladus, you want to call this Enceladus, or one of these rocky ones, they come from deeper down inside. And that could explain some of the geophysical distinctions between the various middle-sized moons. Enceladus, of course, being the one that's eruptive, and Tethys being one of the satellites that's almost pure ice. And then heating, this is kind of interesting, is because the event deposits a fair amount of heat on one side of Titan when it's all done. You have raised the temperatures internally at about 500, by about 500 Kelvin. So we've just started exploring this scenario to see if it makes geophysical, and I think fundamentally dynamical sense. I think that's where we need to be concerned with. But to conclude, pairwise accretion, it's a messy thing. It just doesn't pop two planets together and make a third. You do a lot of crazy stuff, and so it causes us to have some caution in how we interpret planetary compositions. You can strip and swap material. You can liberate mantle and crust in these kinds of slow events, creating Mercury. You could imagine an Earth-like planet accreting in a solar system with a bunch of super-Earths. The Earth-like planets that survived that accretion may likely have had one or more hit-and-run events that would have ripped their mantles off or ripped their crusts and atmospheres off. And so there's some implications for exoplanetary systems. And I think that the diversity of planets that are predicted by this model, you should have a diverse number of different kinds of places in the universe. You should have not just one kinds of planets forming of one different size. You should have a high diversity. And of diversity, as far as I know, from my little understanding of biology, and this being a SETI talk, I wanted to conclude with this notion that increasing the diversity of planets in the universe is a way of increasing the possibilities of life. So thank you.
Erik, if I could start with one question. In your plot where you had velocities, I think you know the one I'm talking about. That
this
one.
one.
That one. So what does negative accretion efficiency mean?
Oh, that's just disruption. That's you're starting to remove mass. So
and that's just being flung off out of the system?
Yeah, so when you start to get out to high, like when we think of catastrophic disruption of asteroids in the main belt today, you're down here on the plot, way down over here. And so when you get to the negatives, you're basically the biggest mass that you end up with is smaller than the biggest mass that you started with.
Okay.
What's it mean when it's 1-to-1?
Equal.
Yeah, I understand that the impactor is equal to the target, but then what does accretion efficiency of 0 mean under those conditions? That means one of the two is completely destroyed and the other one is 100% retained? It couldn't mean that.
It's on a case-by-case basis, you'd have to look at it, because all we really did is did clump detection and said, what's the mass of the biggest final clump versus the biggest mass prior? And so it could mean that things were horribly destroyed.
No, there could be two of them.
Yeah, there could be. Yes, there could be
two of them
yes,
of size
yes.
1. I get
yeah,
it.
and in fact, I think you're right. For a 1-to-1, it would be symmetric, and you'd get two objects that are the same size. Yeah.
Thank you. Your talk gives us a really nice compendium of the many kinds of collisions that can occur. One question I have is that, can you scale some of this research up to, say, even producing a general solution to various classifications of different kinds of protoplanetary disks and their compositions and size of objects, and then run them forward in simulation to, on the one hand, produce types of solar systems that only have large bodies like our solar system, versus at the other extreme range would be something like what you're working on is the Saturn ring system, in which you have only small bodies and lots and lots of them. So that you have a situation where maybe the balance between fragmentation from collisions and the development of larger bodies due to accretion, can be worked out, and maybe you have a whole system of planetary disks that can produce different kinds of results.
The exoplanet searches are telling us a lot about You have silicate-rich debris disks, which indicate planets that somehow collided and came apart. I think the general question, can we run these forward models in time and look at branching off points? I think it's a fundamental question, because there probably are, aspects to, how did our solar system branch off? Maybe something had to do with how it melted early on, which differentiated bodies, which might have changed how they collided. I mean, there could be some dynamics at play. The real issue here is we've treated it as sort of separate problems. Like, I'll take a collisional model, you run an n-body code. When you have a collision, give me a call. I'll give you the result. You plug it into your code. There's two problems there. One is that there's a lot more parameters, like spin and things, so the handoff isn't as elegant as we'd like. But the other problem is that n-body codes have a hard time tracking more than maybe 60 bodies to very late time, maybe 200 bodies. So that's, I think that's a key point, and that's something that's being worked on by, among others, Genda and Kakubo in Japan are looking at, having an automated structure of modeling n-body codes. When they get a collision, they run an SPH simulation and then plug it back in. But then they just spawn more bodies than they can keep track of. So
this is Ignacio Mosqueira. I actually gave, Paul Strata gave a talk for me at Cornell on the origin of the rings.
Mm-hmm.
And the issue there is really whether the formation of the rings of Saturn was primordial or was at the time of the late heavy bombardment.
Mm-hmm.
That's the first thing to decide to begin with. There's there are many reasons to think that the origin of the rings has to be late.
Mm-hmm.
Because whatever you do, if you manage to produce moons that are icy and then you insist in making the rings early on, then you still have to deal with contamination. And whatever you lose moons, we talk about spiraling of the moon. This is the Knapp work, which doesn't seem very realistic, because if you lose the moon, then you have to decide how you survive the ring. In any case, for a variety of reasons, the thing to do is to think that you're making the rings at the tail end of the bombardment. And in that case, you separate the two questions. There are actually many mechanisms that can produce icy moons, but the rings are not connected to the origins of the moons.
That's right. I think I agree with that. I think you populate. You can. I actually like the scenario of a moonlet disruption. Something that happens quite late. This is basically a way of if the scenario is true that the late heavy bombardment stripped most of the ice out of the Saturn system. If that scenario is true, then where do you find ice? Well, you find it in the mantles of these planets. How do you liberate the ice? You can liberate it in this manner. So it's a scenario that's on the table. The thing that really motivates it is that you've given a lot of these things are escaping. Some of these become satellites of Titan, but these escape, and they go on their own dynamical pathways. Many of them crash back into Titan. Many of them crash into Saturn. Many of them reaccrete, forming a new family of bodies. And then those. One of the appealing things of this scenario is there's this paper by Levison and Kevin Walsh and colleagues where Iapetus, one of the inner moons of Saturn, actually has this walnut shell ridge around it. And their solution to this, which I think is a very elegant solution, is that Iapetus had a satellite. It had a satellite that had a satellite. And this goes unstable after some time and collapses and breaks up into a ring. And that ring drapes itself over Iapetus. It's an elegant explanation, and what's kind of cute here is that you have a number of these that have satellites around them. So,
Iapetus is an outer satellite.
True, yeah.
Talking about the rings, and for the
Yeah,
rings, how
well.
to make an icy polar.
Yeah.
Ideas a long time ago.
Sure, yeah. No, this is just this is a scenario. These are numbers, zeros and ones being added and subtracted, and I think we have to recognize that. But it's I think kind of a novel aspect of ice production. I wouldn't say ring formation. It's ice production and populating worlds that are 500 to 1,500 kilometers diameter in such a manner.
Hi. Could the delayed solidification of the chondrite be due to being exposed to so much hot black-body radiation by surrounded hot droplets that it just takes longer for it to be able to radiate out and cool?
The idea for cooling times in this model is that this plume, so you're looking at a snapshot at 0, 1 hour, 2 hours roughly. And this is still highly opaque. And so the scenario that we've got for chondrule cooling time here is that you've got this plume now of droplets that are smaller than chondrules. So it's kind of like a rain cloud. And then those droplets are interacting and merging. Some of them you might have records of their collisions. And then when does it cool? Well, it cools when they've accreted to a size that their opacity drops, because there's fewer of them. Surface area drops, and then they can radiate to space, and then they cool. And so the cooling that's going to occur in this plume is going to be controlled by the dynamics of plume expansion. And the dynamics of plume expansion is controlled by the dynamics of the collision. And so to first order, this plume is expanding at about the collision velocity. And that gives you an expansion rate that's of order the gravitational time scale. The fate of this can be very complex. We have other scenarios here's high angle, shallow angle, high energy. Some of these end up reclumping after a few hours, and you can imagine chondrules cooling and then clumping back into piles. A lot of this material drapes back onto the target, so you can imagine a target that's encrusted in chondrules by this process. And then a lot of these escape, and you can imagine now naked chondrules plowing through the nebula to do their own crazy thing.
Okay, so we have to make way for the next meeting in this room. So if you have any more questions, I encourage you to come up and speak to Erik. Erik, thanks very much for your talk. Here's a SETI mug in commemoration.
Hey, thank you.
Please join me in thanking Erik for his great talk.